The first configuration we're going to look at for our Schmitt trigger circuits is our basic inverting configuration. So as you might be guessing, we're using our op amps. It's going to be similar to our op amp circuits we have seen previously where we had inverting and non-inverting configurations. So just as a useful reference, I've copied from our previous video our comparator as well as our input-output voltage relationships in graphical form for your reference. And before we look at analyzing our Schmitt trigger circuit or even what it looks like, I want to mention that the creator of this goes by the name of Otto Schmitt. And so Otto Schmitt developed the Schmitt trigger circuit while he was in graduate school and working on squid nerves and particularly trying to do data processing on impulses from squid nerves. So just a little random trivia for you there. Okay, so what does our actual Schmitt trigger circuit look like? Well, we know we're going to be using an op amp. So we have our op amp with our inverting and non-inverting terminals for our inputs, our output here. And we know we're also going to have positive feedback. So we're actually going to have just our input going into this inverting terminal. We're going to have a resistor R1 connected to our non-inverting terminal. That's going to be to ground. And then our positive feedback means that the connection between our output and our inputs is happening at our non-inverting terminal. So in the past, in previous classes when we've looked at op amp circuits, we had our output connected to the inverting terminal or our negative terminal. And so for that reason we called it negative feedback, but in this case we can see we're dealing with positive feedback. And so this resistor we're going to call R2. So in order to aid our analysis, we can also identify this voltage here as V plus, or the voltage at our non-inverting terminal. And so we can use voltage division to say that V plus is equal to R1 divided by R1 plus R2 times V out. And so if anybody has any issues seeing that, or maybe you need a little refresher on your basic circuit analysis, please let me know and I'll be happy to help you out. Okay, so we already know this is a bistable multivibrator, which means it has two stable states. So because it has two stable states, we're going to have to make an assumption about what our V out is over here before we can do any analysis. So let's start by assume it's in a high state. So let's assume that our V out is equal to VH. And so remember, VH is our saturated input on our upper side. And to keep things simple right now for our derivation, let's assume that VH is greater than 0. Well, so what that means then is that our V positive, the voltage at our non-inverting terminal, is going to be equal to R1 divided by R1 plus R2. And now we're going to plug in for V out our VH. Okay, and so now just based on the general properties of our comparator, which we can see here as a review, we know that for as long as VI is less than V plus, our output is remaining high. Okay? So that means it's staying at VH. But we know from our comparative chart that eventually if this input keeps changing, then we'll eventually switch over to a lower voltage. Well, what we're interested in is where that transition occurs. And so our transition is actually going to occur when our VI is equal to V plus. Okay, and just to make things easier, we're going to call this voltage VTH, and that's going to be our high threshold, we'll call it. So VTH is our high threshold. And what we can do is we can say, well, this is our voltage where our input voltage is equal to VI. And so we're going to call our input voltage, this is going to be our special case, our VTH. And we know that occurs when it's equal to V plus, which we just up here said that our V plus is equal to R1 divided by R1 plus R2 times VH. So this would be the equation for our high threshold. Okay, so what we can do is we can go ahead and plot this. And so let's put our plot here, and we're going to come back and we're going to consider our other case here in a little bit. Okay, so a couple key voltages and values to label. We of course need to label our V high and our V low. Those are our two saturated output levels. And this is our V input and our V output. Okay, so now we just calculated this value VTH. We've said we're assuming that our VH is positive, so that means that our VTH is going to be positive. So let's put it somewhere over here. And so this is going to be our VTH. So what we're saying with this is to put all these words in graphical form. We're saying that so long as our input is less than V positive, then our output is going to be high. So over here, we have an output that looks like this. Now, as soon as we reach this threshold point, that's where we switch to being low. So once we get to VTH, we now come down here, and as we increase our input voltage, we keep on going this way. So we've moved in that direction. So we're going from a low input to a higher input. So we get something like this. Okay, so now let's consider the opposite case. So let's say instead of assuming that our Vout is high, let's assume that our Vout is low. Okay, assume Vout is low, and again, for simplicity, we're going to assume that that is a negative value. And still from our voltage divider, we have that same relation that our V plus is equal to R1 over R1 plus R2, but now our V output is V low. Well, so now from our basic comparator operation, we know so long as our input is above that V positive, that our output is remaining low. So our output remains low at VL. And so just like with our high case, we're interested in that transition point. And so we know the transition point based on our comparator is where the two inputs are equal, the two inputs that are one at our inverting input and one at our non-inverting input. So when those two are equal, we're going to have that our input is equal to V positive, and we're going to call this our VTL, which is our low threshold. So VTL is our low threshold. So we can say our VI is equal to the special case for our transition point is VTL. And we know that's just equal to our V positive, which we had written up above right here, is R1 divided by R1 plus R2 times VL. So here's the equation for our low threshold voltage. Okay, so we said that our VL is negative, so we know that this VTL is also going to be negative because we're just going to have positive resistor values. So we can come up here and somewhere negative input voltage, we can label our VTL, our low threshold. Okay, so now let's consider what we were talking about here. We were talking about as long as our input voltage is greater than that transition point, it's going to stay low. So now what we're saying is if we're coming this direction with our input voltage, it's going to stay low, and I should be going through that VL, until we get to our VTL, and that's our transition point. So once we reach VTL, we're then transitioning to a high value. So notice for this red curve, we're traveling in the opposite direction. So we're starting at a high input voltage, and we're going to a low input voltage. So we get arrows here just indicating our directions on the various curves. And so what we can see from this, our net result is we have this hysteresis effect. And so you might have seen this in some other places, particularly one place you see it is in electromagnets, or in terms of power circuits, you could see this in transformer characteristics. various places in electrical engineering, but we have some hysteresis effect. And so what that means is we can think of really this circuit now has some rudimentary memory. So how is that really memory? Well, if we think about sort of this intermediate region here, it has to know where it was at before in order to know whether it should be high or low. If it's coming from a lower input voltage, then it's going to stay high. Whereas if it was coming from a higher input voltage, it would be low. So we can consider this circuit as having some memory. So one thing to note too is that in this particular circuit, I've drawn this such that our magnitude of my VH high and VHL are approximately the same, and such that my VTL and VTH are approximately the same. That doesn't necessarily have to be true. We can think about shifting this square up, down, right, left, sort of squeezing it to make it narrower or widening it to make it larger. And so one good place to look is on page 1089 of Niemann. There's a good example. So example 15.6 has you sort of work through how to design a circuit to get a certain hysteresis width. So the hysteresis width is essentially what we're calling this width here between our VTH and our VTL. So that would be our hysteresis width. So another good question to ask after you work through that problem is how could we adjust that hysteresis width? And so what you could see by looking at the equations is that by adjusting values of R1 and R2, we can make that gap between VTL and VTH smaller or larger. So that I would encourage you to look through that example and let me know if you have any questions.